thank you, Dr. Low. Can you hear me? Okay, all right, okay, that's good. And his mic is working, that's good. Thank you again, Dr. Low, for the introduction. And I also would like to thank, Dr. Chen, director, of your institute, Dr. Chen Yilu, for inviting me here to give this lecture. So this is my great pleasure to have this opportunity to talk to you about some of the work that we've been doing. Actually, this is all my students' work. All those, Yang Han, Wida Po, San Zitong, Wang Wakaria, Dong Zhiwu, and myself. Those are all my current students. I'm mainly with the Department of Chemical and Biomolecular Engineering, but also a joint appointment with the Department of Material Science and Engineering. Okay. Eh? It looks it's not working for some reason. Let me see. Maybe pointing here. No. Yeah, with the slide. I'm going to change the slide. Right? Oh, okay. All right, okay. Very good. Thank you. Let me see. Huh? Oh. That looks not working yet. Okay. Oh. Let me see. Looks is not working. Let me see. Oh, okay. It's working here now. Thank you. All right. So here's the outline. I will talk about several kinds of membrane. The first one is the CO2 selective membrane for hydrogen purification for fuel cell, and also for carbon capture from flue gas in the coal-fired power plant. And then I will move into the water purification membrane, including reverse osmosis membrane for water desalination, and also the supported liquid membrane for antibiotics and heavy metal removal and recovery. Okay, as you all know that fuel cell is an energy efficient and also clean energy converting device, but however, still need very high purity hydrogen, in order to get a fuel cell to work, particularly for the proton exchange membrane fuel cell, because most of hydrogen coming from syngas. So we do need to have a quite high purity of hydrogen to get down to less than 10 parts per million carbon monoxide. And for hydrogen sulfide, we like to get down to less than 10 parts per billion in the hydrogen product. So it is quite a challenge for fuel cell application. So our approach is to use CO2 selective membrane to remove the CO2. Then we can increase the concentration of hydrogen, in the syngas, and also for the hydrogen concentration purity. And as you know, the water gas shift reaction is a reversible reaction. But however, if we remove CO2, then the reaction will go into the right side, with the right hand side, produce more hydrogen, okay, from carbon monoxide and the steam. So this approach we're taking, we remove CO2, then we can get almost all the carbon monoxide to be converted, to make hydrogen, and then to increase the purity. So we hope that we can achieve the carbon monoxide to less than 10 parts per million in the hydrogen product through the CO2 removal, and also reduce the hydrogen sulfide to go down to less than 10 parts per billion through the hydrogen sulfide removal. Here, showing the membrane can contain both fixed site and mobile carrier, the carrier that allow CO2 to go across the membrane. The fixed site carrier, for example, would be the polymer that contain the amino group. Okay, I will talk to you more about the CO2 amine reaction. But so that CO2 can react, with amino group that's already incorporated inside the membrane. But if those amino group are attached to the polymer chain, for example, the polyamines, okay, then the amino group cannot diffuse because it got fixed to the polymer chain. But however, the reaction product can hop from one amino site to the next amino site and go across the membrane. But we also incorporate so-called mobile carrier. Those are small amino compounds. Because molecule size is small enough, so can diffuse, from one side to the other side. So again, the reaction product, then essentially reaction product between CO2 and mobile carrier, and then they can diffuse across the membrane. And certainly there's also third way that for CO2 to go across the membrane, that will be going through the so-called solution diffusion mechanism. That going this physical phenomena that CO2 can dissolve in the membrane, and then the dissolved CO2 can then diffuse across the membrane. So there are three ways that we can get the CO2 to go across the membrane. But majority they come from the mobile carrier and also fixed site carrier. The percentage through the solution diffusion mechanism is very small. It's less than 1%. Okay? So more than 99% goes through the mobile carrier and fixed site carrier. And for the non-reacting gases such as hydrogen and nitrogen, because they cannot react with amino group, so they can only go through the solution diffusion mechanism to go across the membrane. So therefore, their flux going through the membrane is very slow. So we can obtain very high selectivity between CO2 and either versus hydrogen or nitrogen. So here is the slide on CO2 amine reaction. Generally, we can classify amine into unhindered amine and then sterically hindered amine. For example, when we have this more ethanol amine, that would be the unhindered amine because this ethanol, this group is linear. Okay, so not much of a steric hindrance. Versus the steric hindrance amine, I give you an example over here. The amino group is attached to a tertiary carbon. Okay, and then certainly you have those methyl group, right adjacent, to this nitrogen site, like the nitrogen. So this could provide the steric hindrance to the nitrogen site. Okay, so when the CO2 react with amino group, normally described as going through the Zwitter ion mechanism. Means the CO2 is added to the nitrogen side, and then form the Zwitter ion. Means it cannot carry both positive and negative charge, ion. Okay, it's called Zwitter ion. Then that require another amino group to obstruct the proton from the sweeter ion to form the carbamate ion that carry the negative charge. Okay, and then so then this amino group become protonated. Okay, so if we add those two reactions together, it will give you this reaction over here, and that is the reaction, pathway for the unhindered amine, because the carbamate ion is stable. Okay, so that require two more amino group in order to capture one more of the CO2. But however, if you introduce a bulkier group, such as the tertiary carbon, to the nitrogen side, then the carbamate ion is not stable because of the steric hindrance, surrounding the nitrogen side. Then the nitrogen COO bond, cannot rotate freely. Whenever this nitrogen COO bond rotate, they're going to hit the methyl group on the side. Okay, so therefore the carbamate ion is not stable. When the carbamate ion is not stable, they will react with water. We all know the water is everywhere, even including in this room, right? In particular in the summertime, we are high humidity. So that can capture the react with water, and then can form bicarbonate ion, as a sink for the CO2. Then that also regenerate amino group. So if we add those reactions together, you will require one more amino group to capture one more CO2. And that is the theoretical maximum, CO2 absorption capacity for an amino compound. That would be the steric hindered amine. Okay. That's one advantage to convert the amino group into steric hindered amine, so they can double the capture capacity for CO2. In terms of role of water, as we say, the water is in all the gases that we encounter, okay, even including the air. So the water can also obstruct proton, okay, but however, its ability is not as effective as another amino group, okay. But however, water can swell the membrane, swell the polymer, and that can increase the flux, through the membrane. All right, my student start with polyamine. As you can see over here, this amino group is attached to a linear chain. So this, by definition, is unhindered amino group. So we make a membrane, based on the polyamine. We only obtain about selectivity of 20 between CO2 and hydrogen. And then the CO2 permeability, which is a measure of how fast CO2 can go across the membrane, then that is only about 50. But however, when we modify this unhindered amino group into hindered amino group, essentially we insert isopropyl group to this nitrogen side, and we convert from an unhindered polyamine into the moderately hindered polyamine attached with isopropyl group. You can see immediately the selectivity is double, and then the permeability increased by a factor of 5 to 6 times. Okay, so very significant increase. The reason is based on the chemistry we just went through. Because this absorption capacity is one more of this amino group can capture one more of CO2, versus here require two more. So therefore, we have a more free amino group inside the membrane, so to capture CO2. That's why the CO2 can go across membrane, much faster. Then if we change this bulkier group to even bigger group, tertiary butyl group, then the result is somewhere in between. The reason is that, even though we still only require one more amino group to capture one more of the CO2, but however, because the amino group is more sterically hindered, so more difficult for CO2 to react with amino group. So the reaction rate is reduced to some extent. But because we have more free amino group, so overall performance is still better than the unhindered polyiodine. So we here is the summary of a lot of data that published in the literature. Particularly, a lot of membrane people have synthesized based on the solution diffusion mechanism, and also earlier work people have done on the Frigidaire transport membrane, and then versus our more recent result, including the Frigidaire transport membrane, with based on polyamine, and also Frigidaire transport membrane that with this isopropyl group modify the polyamine. So we push this performance, amide, to as high selectivity and also as high permeability we can. Okay, we continue to work in this area with that to further improve the performance. So recap here for the unhindered amine, so require 2 amino group in order to capture one more CO2. And then, so this form the a stable bicarbonate ion. Then for the hindered amino group, they only require one more and form bicarbonate. So all those they all form chemical bond, okay, in order to capture CO2. But however, the reaction between hydrogen sulfide and the amino group is through the proton transfer, almost like an acid and base type of reaction. Okay, proton transfer here into the amino group and then form the hydrosulfide ion. So the proton is very small, so it's not affected by the steel kinetic, and because of a small proton moiety, so reaction rate is very fast. Typically, this reaction is about 3 times faster than the reaction with CO2. So for our membrane result, now we also show that indeed the hydrogen sulfide, the permeability is about 3 times of the CO2 permeability going through the membrane. For the temperature range we look at, from 110 to about 140 degrees Celsius. And use the membrane that we have synthesized, we are able to reduce the hydrogen sulfide about 50 ppm in the syngas to go all the way down to about 10 part per billion, 10 ppb. So essentially, we can remove all the hydrogen sulfide, and then we can use the syngas for other applications that may be hindered by the presence of hydrogen sulfide. All right, so we do have a machine, a pilot machine in our laboratory that we can scale up the membrane. So you can see over here, this roll to roll, and then going through the oven, drying, and then come over here. You're seeing the membrane sample here is about 14 inches wide. And actually, the machine can handle up to about 21 inches wide, which is about half of commercial membrane size, width. Okay, so we use this machine to scale up, our membrane. We have done quite a lot of scale up run. We typically make 14 inches wide. We can make 600 feet. And then, as I mentioned, our machine is capable of going up to 21 inches wide. For next phase of a scale up, we can also use this. Okay, so we have in the laboratory, we make a membrane with thicknesses of about 15 to 16 micron. And then CO2 permeates in the unit of a gas formulation unit. Then we can obtain very close to 200. And CO2 hydrogen reactivity is also about 200. When we use our pilot machine, we make about similar thickness. And then the CO2 permeance is also in the same order, actually very close. And reactivity is also, quite, close. So we are able, essentially, we can almost directly scale up from a laboratory to the pilot site. For the CO2 capture, as we all know, in the flue gas, the pressure is low, on about 1 atmosphere, right? And the CO2 concentration is also relatively low. If we use natural gas for power generation, then the CO2 is about 6%. Then if you use coal, it will increase to about 14%. But because the pressure is low, concentration also relatively low, so drying force is quite low. So there's no any single stage membrane process, that can achieve DOE's target, Department of Energy target. So the DOE target is to capture 90% of the CO2, not capture the CO2 product, must have a concentration of 95%, or higher. And then the capture cost in 2007 dollar is less than $40 per metric ton of CO2 capture. Okay, and the reason why DOE said actually this is a DOE target for us to achieve, by 2025. So we still have another 9 years, to achieve this. But okay, so the reason DOE said this target is you can use this CO2 for enhanced oil recovery. And what they are paying for CO2 right now is about $40 per ton of the CO2. So you can make money by capturing the CO2 and then use it for enhanced oil recovery. DOE also have another target, so no more than 35% increase on the cost of electricity, but no one can achieve it. Okay? Right now, realistically, is about 60% increase, on the cost of electricity. All right. So in order to achieve the DOE target, so we come up with a membrane structure that certainly we have a non-woven fabric, something like made of a PET, polyethylene terephthalate, just like the one we are wearing, for polyester. And this non-woven fabric as a mechanical support. Then on top, we use a pore size with another polymer there, but this about 50 micron thick and pore size about 70 nanometer. Okay, so this pore size is very big. This pore size is more than 0 micron. And then we with this we can deposit the other nanoparticle there on the top. Okay, so about 250 nanometer, thick, and then inter-particle pore size is about 15 micron. So effectively, we can reduce the pore size from 70 nanometer to 15 nanometer. So that way, we can reduce the penetration of the top polymer layer that can serve as a selective layer for CO2, separation. So here we use the other nanoparticle is about 40 nanometer particle size. And then the selective layer on the top is a dense layer, could be about 200 nanometer. Okay. So initially we make a polyether sulfone. Okay. As through our machine we have the roll-to-roll operation. We make, as mentioned, we make a 14 inches wide. Okay. And then here is the top view of SEM. It's about 70 nanometer pore size. We use this as a substrate. Then we can deposit the other nanoparticle on the top, and then we put the another polymer layer on the top. So here we have this 14 inches wide polyether sulfone porous substrate. We can deposit the other nanoparticle here. Okay, that we can deposit here. Okay, going on. And then after that we coat a layer of amine containing polymer on the top of the other nanoparticle layer that we deposit. Okay, then that's how we make a membrane. So here is the top view of those nanoparticle, the other nanoparticle. It's about 40 nanometer. So the interparticle pores is about 15 nanometer. But certainly you can see there are some defects, but it's not bad. It's within about one particle size. It's about within 40 nanometer, which is really small. And then we have let me see, how do I get rid of it? You can get it on the side over here. This one, I don't need it. Okay, so here, top view here is cross section, where the nanoparticle, nanoparticle over here. That's about, as I mentioned, each particle is about 40 nanometer, and then about 200 some nanometer thick. Thank you. Okay. And then the underneath is much more open, polyether sulfone support. Okay. So okay, here is the whole composite membrane. So again, we have a nylon fabric down over here, and then we polyether sulfone here, and then we white, deposit the nanoparticles here, and then we have amine cover there, on the top. Okay. So we also scale this one up to 14 inches wide, as mentioned, and we have some we coated the amine selectively directly onto polyether sulfone. Okay, and some we have the white nanoparticle, in between, and so we can here, okay, depending on the coating speed, and we can control the membrane thickness. So the higher the coating speed, because we control the solution, delivering rate for the membrane fabrication. So the higher the coating speed, we can get down to thinner membrane thickness. We can get all the way down to about 155 nanometer membrane thickness. After we make a membrane, we can roll this, into so-called the spiral wonder membrane element, and then we put the membrane element inside, membrane module. Okay, because the pressure is very low, we can use a plexiglass, housing, for this. Okay, so the housing allow for fluid to come in and fluid to go out, and then sweep fluid, sweep gas go in and sweep gas, to come out. Here the PE slide, let me walk you through we plot the CO2 nitrogen selectivity versus CO2, permeance. And initially, the performance was not really that good because well, my student needed with time to learn how to make a spanner one membrane module. And we got to glue it and then allow leakage. That's why the performance is not really that good. But eventually, it took about 10 months. Eventually, we got it, okay? We are even the prototype module, we can achieve very high selectivity, more than 200. Actually, we only need about 140, selectivity, then we can use for the CO2 capture. And then the permeance we got up to more than 800, GPU, which is pretty good. Actually here I do related, it would cost about $42 per ton of CO2 capture. If we have about 750 GPU, and so this is in $2,007, but without including the 20% process contingency. What the process contingency means is because it is a new process, and because there's an uncertainty involved, because not too many people have to know what is usually, okay, stay in our laboratory. And so that's why they add the additional cost of 20%. So if you have here, if you, 42 some dollar, you add another 20%, it will become 50 some dollar, $51, $52. But our membrane can get up to way close to $40 per ton. So if you add another 20%, you're going to get up to about $50, in the order, okay? And then, but there are some laboratory results we are able to obtain even higher performance. Then the cost can go down, low. Okay? So at least give you some idea about how much it costs. Okay. But okay, let me pick up a little bit. So so far we all run at the 57 degrees Celsius, which is the typical flue gas temperature. Okay, and but if we run at a higher temperature, so if we control the flue gas temperature, which can be done through controlling the temperature of flue gas desulfurization unit, if we can control that, and let's say at a higher temperature, then our performance increase, almost double. Okay, you can get up to close to 1800 GPU. If 1800 GPU, the cost is going to drop down to $36. Okay, but still $37. Okay, still cost some money. But as I mentioned, our original idea is to deposit the zeolite nanoparticle in the porous polymer substrate. Okay, you can see we are deposit those zeolite white nanoparticles. This is the 100 nanometer scale. So those are zeolite white nanoparticle. Okay, over here. Actually, they can sink into the pore structure. We can use that as a sea crystal. And then we dip the whole thing into the green solution, and it took about 1 hour to grow the zeolite crystal. Here showing the top view, you can see those zeolite crystal on the top of a polymer substrate, and here is cross section. You can see they can grow almost about micron. Actually, here is about this is polymer there, and those are crystals sticking out. Okay, so we can make a zeolite membrane, on a polymer support. As you know, in the past, people can only grow the zeolite on an inorganic substrate, and as you know, by definition, inorganic substrate is not that flexible, so it's very difficult to reduce the cost. Now with this technique, we can cut down the cost, very significantly. Okay, let me switch gear to water side. Start with reverse osmosis. Again, for reverse osmosis, there's also non-woven fabric. Exactly the same thing as with a windsole. Okay, and then also nanoporous polymer substrate. Typically use polysulfone. Okay, different from slightly different from polyether sulfone. And then we can introduce very thin layer about 0.2 micron, which is 200 nanometer. Okay, selective layer on the top. Right. So when we start this project, we recognize the membrane available has very tight membrane structure and highly crossing. The key problem is insufficient hydrophilicity. It means that there are not enough hydrophilic group in the membrane. So therefore, this the water flux was quite limited. So, so what we did is this we introduced the hydrophilic moiety into the membrane structure. So during this makes through the so-called interfacial polymerization, which was invented by Jiang Kada, at the Dow Chemical. And so our contribution here is, during the interfacial polymerization, we incorporate the hydrophilic compound, in the amine solution. So we take a polysulfone nanoporous support. Here the surface porous structure. So we coat, amine solution there, or to free up those porous structure. We put a coating of amine solution in there, and then we contact these with hydrocarbon solution that contains the acid chloride, then to do the interfacial polymerization to make so-called interfacially polymerized, aromatic polyamide membrane. Okay. So the additive, we have identified 6, groups of chemical compounds. One of the group represent here that also contain the amino group. Okay, and then but also with carboxylic acid group, but because of a reaction, so we have neutralized this with triethylamine. Okay, so these carry the negative charge, right? So and also very hydrophilic. So these all hydrophilic additive, and that also provide the charge rejection for salt, which is charge repulsion for the charge rejection. And this amino group would allow us to incorporate this compound onto the membrane. Okay. So what we have again, we have this meta-phenylene diamine. Okay, and then we also this is in the aqueous phase. In addition, we also put this hydrophilic additive, and this is in the water phase, and this is in the hydrocarbon phase. So those two react through the interfacial polymerization, and then we make the interfacial polymerized polyamide membrane. And now, because we add a hydrophilic additive, so this hydrophilic additive can form the covalent bonding, and then attach to the membrane. This whole thing, is the interfacial polymerized, polyamide membrane. So now, with our approach, we can add hydrophilic additive, to the membrane. Again, all through the chemical reaction. Okay, the chemistry is highly involved. All right. So we plot the flux versus the amount of hydrophilic additive that we add in the solution, in the aqueous solution. And so before we add hydrophilic additive, our flux is about 1 cubic meter per square meter membrane area per day. And with addition of the hydrophilic additive during the reaction, we are able to increase gradually. Okay? And then reach to the maximum, when we add more, start to come down. The reason for coming down, as you see, let me back up a little bit. As you can see over here, only these, diamine can form a membrane with AC chloride. This guy, the one hydrophilic additive, only have one functional group, cannot form a membrane, can only attach to the membrane. Those two can polymerate, but those two cannot polymerate. So this can only add to the membrane. So when you have too high concentration of these, going to interfere with the interfacial polymerization. And then when we have too high of these, interference, the membrane is not going to be formed that well. And then performance is going to drop. Okay, that's the reason it's going to drop. So we achieve a maximum, same thing as salt rejection. Quite coincident, is also achieve a maximum in the we can achieve more than 99.4% salt rejection. So with side-by-side comparison, the so-called basic membrane is a membrane that's available commercially. That was invented by Jiang Kadan of Dow Chemical. And then our invention is called a high flux membrane. So you can see for the flux, we can increase quite significantly. Okay, and the salt rejection is about the same. And then, but however, our contact angle is low. It means more hydrophilic because we add the hydrophilic additive into the membrane, and that can have an influence on membrane volume. All right. So here the stability test. We use the seawater from Port Vainini. That's in California, by Los Angeles. Okay, and that's one of the Navy sea base. This project was sponsored by Office of Naval Research. So it looks really very stable, for the flux and also salt rejection. We run for about 30 days, and then after that we use the FTIR. So you can see the two major groups, for the polyamide group have two major characteristics, absorption peak in FTIR. So before the 30 days stability test, or unused membrane, we did the FTIR. Then after 30 days, we did the FTIR. Practically, we cannot see any, difference. Membrane, quite stable. And in terms of flying, okay. For some reason, this come up again. In terms of flying, thank you. Now, okay, that means when we use a synthetic seawater, that has 3.28% of sodium chloride. Okay, and so we obtain this flux for the basic membrane, and then for the high flux membrane, we have much higher flux. But when we add the 25 ppm of a sodium genet, which is the decomposition of seaweed, when seaweed decompose, and then you're gonna, sodium genet, and that's a very common falling in the seawater. 25 ppm, so then for basic membrane drop 18%, but for our high flux membrane only drop 11%. And when we double the foreign, 50 to 50 ppm, drop more. So that here also drop more. But overall, our reduction is still much, lower than the membrane without the hydrophilic additive. Okay, so that is the overall observation. But in terms of equation, okay, we can express the flux, proportional to the drying force, which is applied pressure subtract the osmotic pressure, okay? And then divided by the solution viscosity, and then there's sum of resistance, going through the membrane. One is the membrane by itself, resistant, right, for the water to go through. Another resistance comes from the fouling. When you have a foreign deposit on the surface of membrane, that form, a new layer of membrane on the top of a whole membrane, right? And that also provides resistance. All right. So then, if there's no foreign, like we put a 0 here, no foreign, and then suddenly this term is gone, right? We just use synthetic water, okay, sodium chloride water without any foreign in there. So this term is gone, right? And then go through the very simple algebraic, manipulation. We can derive the ratio of the foreign resistance for high flux membrane, this term over here, for the high flux membrane, versus the basic membrane, also the same term over here, but for the basic membrane, and end up to be here. But all those are the quantity that we can measure. Then we plug in there, showing we only have a 30%. Foreign resistance, foreign layer resistance for our high flux membrane only 30% of the original, basic membrane. So means the foreign resistance is reduced significantly. Essentially, this term is reduced significantly. Okay, that's why we observe the result. And then we use an atomic force microscope and then measure the surface roughness. So original for the commercial membrane is about 106 nanometer. For the membrane we make it's only 77 nanometer. So roughness is reduced, which is an improvement. So that the rough for the membrane surface is easier to track the foreign on the surface. Okay, so therefore our membranes are more foreign resistant. And that's for seawater. We also extend that to brackish water. Brackish water that contains about 0.2% of sodium chloride. The concentration is much reduced. And then with laboratory size membrane, which is about 3 inches by 3 inches, okay? We obtain a flux of 52 gallons per square foot per day. And then the soil rejection is almost 99%. We scale up 10 times, means scale up to 10 inches by 10 inches. And the flux is still quite similar. Soil rejection also quite similar. And we scale up to commercial size. We rent commercial equipment from a membrane company, and then we provide the funding. And we make a 42 inches wide, wider than the machine I show you, about twice as wider. And then make 1,000 feet, okay? Again, our flux is, from the laboratory all the way to commercial size, they are all quite consistent. Not many membranes we can do it, but this is one of the membranes. We're quite fortunate we are able to scale successfully. And so we use the membrane that we make to make into spiral one that the airmen. We make 12 of them, okay? Each one is a 4-inch diameter, and certainly would be the 40 inches long, right? When you lower it up. And then each one has a 82 square foot membrane area. And for each element, we can produce 4,300 gallons per day of water. So if you take this number divided by this membrane area, you obtain this flux. Okay? This is identical to what we have obtained in the laboratory. And then soil rejection also quite good. Then the Bureau of Reclamation, they took our membrane, then test at the brackish groundwater National Desalination Research Facility. They looked at alphabetical soup, very, very long abbreviation. This happened to be in Alamogordo, New Mexico, where they have a water shortage issue over there. So their groundwater is very salty. It's a brackish water. Okay. So they did a test. Essentially, it's an independent third-party evaluation of our membrane, and they confirm our high flood, comparing with the base membrane available in the market today. All right. I'm getting to, I see my time coming. I'm getting to my last subject, supported liquid membrane, which is really the organic, solution embedded in the pores of a microporous support. You know that commercially you have a microporous polypropylene hollow fiber. Okay, that's commercially available. And so in this porous, structure, we incorporate embedded, organic solution in there. Now, organic solution contains a complexity 18. I will get into it. So you will, for example, your wastewater coming in to one side of a membrane, and then suddenly the pollutant is then extracted into the stripping side, and then after the treatment, they can discharge. Then this stripping solution, suddenly can accumulate those pollutants in there, or the compound that you want to, separate. Okay, and then so because here we can combine the extraction and stripping, typically is done in two separate steps in the commercial typical conventional operation, such as solvent extraction. But here, with the support liquid membrane, we can combine those two together. So therefore, we can overcome the thermodynamic, equilibrium limitation, because this is a kinetic process. We extract, then we strip, just like a membrane for CO2 separation that we went through. Okay. So this worked very well. Actually, this work was started in 1960. A lot of people working on this. But however, they could not really, get the membrane to be stable. The reason for that is because the organic solution embedded in the microporous, support is very small amount, and then the emulsification from the shear force can remove the organic solution. Then osmotic pressure can also push, this organic solution out from the porous substrate. So, so none of those really got commercialized until we got involved. Okay. So what we did is, we dispersed our strip solution in the continuous organic membrane solution, and then certainly under the mixing and also under the flow, they stay as dispersion. And then with this dispersion, certainly we have a constant supply of organic solution to the porous structure. So that's how we stabilize this membrane. Okay. Yeah. So here, okay. Let's see. As I mentioned, we use a hollow fiber. This hollow fiber is made of a polypropylene. So porous polypropylene. The pore size is about 300, Armstrong, 30 nanometer. And when we disperse the aqueous strip solution in a continuous organic phase, the particle size is about 100 micron and bigger. So they are so much bigger than those pores, so cannot come from one side to the other. But however, because the polypropylene is organic in nature, and the organic solution is also organic, so that could ship through. The solution can ship through. So what we have to do, we have to maintain this the pressure to be slightly higher than the pressure on this side. Okay, so pressure on this side can be slightly higher than pressure on this side. It's only about 2 psi. Not even about 0.1 and also pressure higher. So we are able to stop the flow of organic solution from one side to the other side, and then we can get into the extended operation then to stabilize this membrane. We have applied this for the separation of penicillin G and sulforection. You can see all those, they all contain carboxylic, acid group, okay? So, and depending on the pH, I'm sure that our Professor Dr. Sunny Chen, also quite organic, there's a biochemical, quite well. All right. So you can, depending on the pH, we can convert this into the charge, the species. Okay. So here, then the sulforection can carry the negative charge. Okay. This is about pH of 2. And then we use quaternary ammonium chloride as a compaction agent. Okay. This is commercially available, called Aliquot. Okay. So we use quaternary ammonium preparation this way. So that can ion exchange. So chloride can come out, and then sulforection, can come in. And then come to this side, we use potassium chloride as a stripping agent. So they can, because the chloride concentration is higher here, so we can strip out. So essentially we are using chloride ion pumping, to drive the separation to extract sulforection from the fermentation broth into the trip solution. Then we can, separate from the fermentation broth. Okay, and so that the trip solution concentration will increase with time, and while the free solution is reduced, and we can concentration will be much higher. And then they agree with our model prediction, really very well. And so here is for chromic acid removal. Okay, so as you know, hexavalent chromic is very toxic. So in the in the drinking water, can be less than few ppm. Okay, and we can use organic amine, to capture, to extract, the chromic acid. The chromic acid come in, actually come in as a whole portion, come in over here. One proton come over here to become this. Okay, and all right. So we can, from the complex, and then come to the strip side. We use the sodium hydroxide, and then as a stripping agent, and because the hydroxide ion is a much stronger base than the amine, and so we can convert the chromic acid on this side now would be the sodium chromate on this side. Okay, the so-called the hydroxyl ion pumping to drive the separation. So if wastewater contains even 50 to 1,000 ppm of hexavalent chromium, we can get down to the HN 0.05 ppm, which is drinking water standard. And on the other hand, we can concentrate to 20% of hexavalent chromium. But based on the sodium chromate, is about 65%, which is concentration quite high. We can use that as a pigment, for the pen. Okay, so we eliminate any secondary waste. And here is for metal ion. Okay, so then we use organic acid, as a compaction agent, and then this side we use a strong acid such as sulfuric acid. So this would be a proton pumping. So let's say if you have a heavy metal or something that the cubic ion. I think I have an example on that. Okay, cubic ion. Actually, this is from Berkeley Pitts water. That's in Butte, Montana. That's one of all copper mining site, and they were huge. They call it a big lake of wastewater. There is about 1 mile wide, and then also 1 mile square, and then 600 feet deep. Okay, people refer that as the biggest cup of a poison in America. All right. So we are able to remove, cubic ion to go down to less than ppm range. So this is, hydroxy oxide, combustion agent. And then the trip side, concentration can go higher than 3,000 ppm. And 3,000 ppm is needed in order to do the electrowinning process to, recover the cubic, the copper metal. Okay, so, and in the body piece water also containing zinc. I may have that over here. So zinc concentration higher, about 500 some ppm. We can get all the way up to about 20,000 ppm, which is 2%. Okay, concentration. In summary, on a CO2 selective membrane for hydrogen purification, we have a synthesized membrane have pretty high CO2 hydrogen selectivity, greater than 200, and then also have a high hydrogen sulfide, hydrogen selectivity. We can get hydrogen sulfide to go down to less than 10 parts per billion. So we can use, then the next step we can use whole water gas-acid reaction, which I do not have the time to talk about here, but we have done that. So we can get the carbon monoxide concentration to go down to less than 10 parts per million. So then the CO2 amine chemistry is the key for this separation. For CO2 capture from flue gas, the all-scale membrane not quite promising for meeting a DOE target, and then so the membrane performance improved, with the higher temperature, because higher temperature will higher reaction rate. For seawater desalination, we can make a membrane more than 95% flux increase, and while we still can maintain the very good salt rejection. Membrane stability good, foreign resistance also improve, significantly. For the brackish water, we can double the flux, okay, and we also with this scale the commercial side, stability is also good, and then the hydrophilic, additive reaction in the phasal polymerization certainly is a key, to increase the hydrophilicity. On the supported liquid membrane with strict dispersion, certainly effective for cycloreduction, recovery and removal of heavy metal from wastewater. Certainly complexation reaction are really key, for here. So I said quite many people. I'm not going to go through all the whole list. Okay, and so many of my students working on this area. Funding comes from Department of Energy, National Science Foundation, Office of Naval Research, and also Ohio Department of Development. Thank you very much for your attention. I'll be happy to answer any questions that you may have.
Very interesting talk, and you can use a very simple organic chemistry to produce some very useful materials for industries. So any questions for Professor Ho? Yes?
Professor, very nice talk. I like your talk, your research a lot. So for hydrogen sulfide, so eventually the hydrogen sulfide is trapped on the amine surface, right? So how you remove those sulfide eventually, or recycle those membrane to be able to trap the hydrogen sulfide again.
Oh, hydrogen sulfide 是我们可以用membrane. Okay, we can use a membrane to separate hydrogen sulfide from syngas. Okay, right. So originally your syngas is contaminated with the hydrogen sulfide. Okay, yeah. And then our membrane allows hydrogen sulfide to permeate through faster than CO2, okay. And also much faster than hydrogen. Okay, hydrogen essentially, can only diffuse through our membrane very, very slowly, but hydrogen sulfide can permeate through very fast. So that way we can separate the hydrogen sulfide, from the remaining syngas. So we keep the syngas, on the original side, one side of the membrane, while we are removing the hydrogen sulfide. So the hydrogen sulfide, after we remove it, then you got to go through the Klaus process to convert into elemental sulfur, right? Klaus process, the partial oxidation of hydrogen sulfide to make elemental sulfur. From the elemental sulfur, you can make sulfuric acid, and you can make ammonium sulfate. That's the cycle. Right?
Thanks.
Okay. So with the removal of hydrogen sulfide, then the syngas can go through the water-gas shift reaction, because the commercial available catalyst based on copper zinc oxide is very sensitive to hydrogen sulfide, easy to be poisoned by hydrogen sulfide. So you can remove, hydrogen sulfide. So practically we can remove all the hydrogen sulfide, and get down to less than 10 parts per billion. Yeah.
Well, interesting.
Interesting talk. In the first system, you have CO2 selective membrane, and I remember you show a plot that you now have a system with higher selectivity and higher permeability. And the higher selectivity, I assume it's due to the amine carrying polymer. But the higher selectivity and higher permeability are due to the same thing, same factors because of the introduction of the amine, because this is a porous membrane.
No, there's
It's
a
not.
dense membrane.
Oh, this dense membrane.
The hydrogen is nearly a small molecule, right? Slightly bigger than helium. Okay, so it got to be a dense membrane.
Okay.
A complete dense membrane.
So the permeability, why the introduction of the amino group will increase the permeability?
Yes. Okay, you are right. The introduction of amino group in the membrane, the increase, both the permeability of CO2 and also the selectivity of CO2 versus hydrogen. The reason for that is that when you incorporate the amino group in the membrane, that allow CO2 to react with amino group. This is so-called facilitated transport, right? So the reaction, you increase the solubility of CO2 in the membrane, right? And then reaction product can then go across. All right.
But I thought this membrane served to remove the CO2 so that hydrogen will go through, CO2 will not.
No, the CO2 will go through, hydrogen cannot go through. Okay.
CO2 goes through, hydrogen cannot.
No, the reason that CO2 can go through is because CO2, react with amino group reversibly. So on the one side, you have a higher CO2 concentration that react with amino group in the membrane. And then the reaction product can then diffuse to go across the membrane. On the other side of the membrane, with a low CO2 partial pressure. So because the amine CO2 reaction is reversible. So at a higher concentration, they react. At a low concentration,
Well, I got confused because I think it was feed, you had more CO2, okay? And now you say hydrogen does not go through.
do not. Hydrogen almost goes through very, very small amount. So we can say that the hydrogen is blocked by the membrane.
So CO2 goes through.
That's right.
So hydrogen stays on this side.
That's right.
Okay.
Because the hydrogen cannot react with amino group.
Okay, so if that's the case, I can understand why the permeability increases as well as selectivity.
Yes, they go together.
Okay, in your second system, the desalination membrane, you introduce these ionic group, these triethylamine carboxylate group, because it's supposed to increase the hydrophilicity.
That's right.
That I understand.
That's right.
You say the salt rejection also increases. I don't quite understand why the salt rejection
Okay.
is because
All right, okay.
it's
Then-
it has positive charge, negative charge. Your salt has positive charge and negative charge. So why the salt rejection can be?
Good point. Let me try again. Okay. The salt is sodium chloride, right? It's a sodium ion positive charge, chloride ion negative charge, right? That's in water, in the seawater, right? Or maybe in your soup. You like to take a very salty, soup. Okay, that's one of the case. And so, in order for ion to go across the membrane, right? They also got to dissolve in the membrane. But now, because the charge repulsion, right? Here I incorporate the negative charge ion in the membrane. So therefore, chloride ion cannot, dissolve in the membrane, right? Because charge repulsion. And the chloride cannot get in, sodium ion cannot get in either, right? They got to go hand by hand, right? Because charge neutrality.
But these, both the positive charge and the negative charge, they come together, right?
Yes, you're right.
They come together. If you have negative charge there, you also have positive charge there. So positive charge attracts the chloride, right?
But you're right. But those, the downward equilibrium, right? The equilibrium membrane, they carry the negative charge. Then you only have a counter ion, it's a positive charge. Okay? So the chloride ion cannot get into the membrane because downward equilibrium, because you only have a negative charge there. When chloride cannot get in,
That comes to another question, that can there be ion exchange so that your sodium replace your trash? That's what I mean, ammonium goes to the other side.
Okay. The key is, in the membrane, I have this negative charge. That's stay in the membrane, cannot go anywhere because the chemical bonded, right? So it means that your membrane carry the negative charge. So therefore, the negative charge ion cannot get into the membrane because the charge repulsion, right? This is Darwin discovered this many years ago. Right? So this help only salt rejection. Because membrane carry a negative charge. So the chloride ion cannot get in. When chloride cannot get in, sodium ion cannot go together. Right? But there are some sodium ion inside the membrane. It's okay. But overall, because chloride cannot get in, so therefore, chloride cannot go from one side of membrane to the other side. Only water, can go through.
You build up a
Huh?
donor potential.
What? I'm sorry?
You build up a donor potential very quickly.
Yes.
Deep donor potential.
Yeah.
So the repellence is the potential.
Yeah, because you carry the negative charge. Membrane is negative charge. So, okay.
It don't need a few ions.
Yeah, that's right, yeah.
Any other?
Good point, actually, a good discussion. I'm sorry, any other question?
Okay, I have two questions.
Two questions. Okay.
First one is that you mentioned that normally the temperature of the flue gas is over 100 degrees. And did you trying to use the membrane at lower temperature? So,
Actually, the membrane performs better at a higher temperature. The reason that, the CO2 amine reaction, right? Our membrane separations involve reaction. That's why so-called the Feuchter's transport is really, we use chemistry to enhance separation. That's so-called the Feuchter's transport, okay? So because of reaction, the higher the temperature, the higher the reaction rate. So therefore, membrane perform better at a higher temperature.
Okay.
But can also perform at a lower temperature, but not as well as at a high temperature.
Okay, so normally you don't need to lower down the temperature.
No,
of the
don't
flue
need.
gas.
We just take a flue gas temperature, come in to 57 degrees Celsius, we just use that. Anything you need to change, you got to pay money for it.
Okay, the second question is what's the service lifetime of this membrane?
Very good question. No one knows. Okay. But based on our performance, the stability test, I didn't show the CO2, stability. Actually, we run for, also 20-some days. Okay. Should no change. So we believe she'll be able to last at least 1 year. Membrane life.
Yes, more than 1 year.
Yeah, good, that's right. But let me tell you this way. The number one membrane, actually it's this way. Some of the membrane I talked today, some have been commercialized. Okay, for example, the supported liquid membrane that have been commercialized, used, okay, for the heavy metal, recovery. And the CO2 membrane is about to be commercialized for fuel cell application. We are scaling up the membrane because one company, the fuel cell company, they want to use it. So that's about to be commercialized. But the CO2 capture for flue gas is going to take a while. I'm joking. Okay, not even our technology can be very good. Also, our Congress, they got to get their act together to work. Otherwise, no one wants to pay the money for the CO2 capture. The only thing we can do right now is capture the CO2 for enhanced oil recovery. Okay, that's only near-term, commercialization opportunity. But for the large scale, CO2 capture from the flue gas, it's going to take quite a while. Maybe I estimate maybe about 10 years. Okay, in order to carbon tax to come in, that's what Europe is doing. The U.S. is following the Europe. Okay, so that's really because this we got to spend money in order to capture CO2. So we got to improve our membrane performance, then reduce the cost to as minimal as possible. Okay, so we still have quite a lot of work to do.
Now, after you capture all the CO2, what are you going to do with it?
Some small portion can be made or used for enhanced oil recovery. Actually, even smaller portion to make your soda, the one soda we're drinking, is CO2. Okay, but those are very small quantity. So majority going to go into the ground formation, about 10,000 feet down, saline formation, where the salt solution can dissolve CO2. It's about 6% CO2 can dissolve in 10,000 feet down and store there. That's one.
You spend all that money and energy just to bury the CO2?
Yeah. Otherwise, otherwise got to come on, academics and French, okay, and biochar, in order to make a carbon negative. We can only get to carbon neutral. We cannot get the carbon negative. You guys can get to the carbon negative. Okay.
Hope so.
Yeah. So most of them got to go into the formation. You cannot go anywhere. You cannot put in the ocean. You got to kill all the fish. Right?
Can't you do chemistry with it?
Oh.
Do chemistry with it, do something useful?
Many people thinking of that way. Okay. How can I say? There are only some niche chemistry, but only very small, and you know what I do. Okay. It's called right now. You got to use hydrogen, okay, in order to convert CO2 to a useful product. But hydrogen is not a cheap chemical either. So, none of those can, break even. No way. So only enhanced oil recovery, you can make a little money. Okay, that's quite unfortunate, but this, nothing is perfect in this world, right? That's one. Second question. What's your second one?
I just asked you the service
area?
lifetime.
Oh, the lifetime. Oh, okay. Okay. Right now, all the commercial membrane we have right now, okay, we have a membrane for CO2 separation from natural gas, okay, and also membrane for oxygen separation, separation of air, okay. All those can last 5 years. And also the desalination membrane I mentioned, also lifetime is about 5 years. They can last 5 years. So we hope our membrane for CO2 capture can last for 4 years. That's our cost estimate. We based on a lifetime of 4 years. We do the calculation. So I think that's quite reasonable.
So the investment cost can be returned?
Actually, this cost is a membrane replacement cost. Okay, right? We have a membrane module, and the housing should be able to be reusable. Only a membrane element inside can be replaced, every 4 years. That's the life cycle, the cost that we use for the calculation.
Thank you. Any other questions? So if not, please thank Professor Hall again.
Very good. Thank you.
And we will have a group photo in front of the gate of our institute. So please move out to the first floor. Thank you.